In this online lecture, we're going to discuss the relationship between wave numbers and the types of bonds giving rise to those wave numbers. And here's what we want to get out of this. Number one, the stronger the bond, the higher the frequency or wave number. We also want to know, number two, the lighter the atoms, the higher the frequency or wave number. And by the way, what I mean here by higher frequency means higher frequency of bond vibration, which would therefore give a higher wave number on the IR spectrum. And we're also going to see number three here, the broadening of an OH absorption band is due to hydrogen bonding. We're also going to see number four, electron delocalization, that is resonance, can affect the wave number of a functional group. And lastly, we're going to see that electron withdrawing or donating can affect the wave number of a functional group as well. So let's go back to our wave number chart here. All we're doing here is trying to explain why all of these bonds peak roughly at these corresponding wave numbers. Notice they all vary. One of the ways we can explain it is using an equation you might have learned in physics called Hooke's law. If you do remember this from physics, you might remember that it was related to a spring. And think about it, it's kind of like how we're conceptualizing bonds in organic chemistry. We're thinking of them as springs vibrating and stretching and bending and wagging. So that's why this spring equation is appropriate. But in our particular case, we want our equation to equal wave number. If you learned this equation in physics, you probably saw it equal to frequency. But remember, frequency and wavelength are proportional. As one goes up, so does the other. Now, hopefully, if you did take physics, your professor derived this equation for you. For organic chemistry, it's way beyond the scope of this lecture. We're just going to accept this equation as true. But what I want to do here is point out some of the variables in the equation and connect them to organic chemistry. Like for instance, in this equation you have an F. In this case, F is equal to the force constant, or in other words, the bond strength. Other items in this equation you have are mass. You have both M1 and M2. For us, these are the masses of the atoms. And remember, every bond technically connects two atoms, so that's why there's an M1 and an M2. Now, with this understood, we can see from our equation that, number one, the stronger the bond, that means the higher the frequency or wave number. Again, what we're saying here is that the bigger the F value is, the bigger the wave number. Let's also look at the relationship between mass and wave number. If you study this equation, you're going to see that the lighter the atoms, also the higher the frequency or wave number. Notice we can see that right here in the equation. We have mass 1 being multiplied by mass 2. Notice that would give a bigger number than what we see in the numerator, which is when we're adding mass 1 to mass 2. This means that the smaller M1 and M2 are, the greater the wave number. Or we can say they're inversely proportional to each other. Let's look at some examples of what we're trying to see here. Notice here we have C triple bonded to C, C double bonded to C, and then carbon singly bonded to carbon. If you remember from a previous online lecture, we noted that single bonds are longer than double bonds, which are longer than triple bonds. So the trend is, as we move up, we go from a longer bond to a shorter bond. When we first learned this, we also learned this relationship as well. That is, the shorter the bond, the stronger it is. Which means, again, the trend here would be weakest on the bottom to strongest bond on the top. And what we're trying to learn in this online lecture is the relationship between bond strength and wave number. And we saw through Hooke's law that this would be the relationship here, that the C singly bonded to another carbon would have the lower wave number and the C triply bonded to another carbon would have a higher wave number. Another way you could think about this is, remember, if triple bonds are shorter, we could think of them as tighter or stiffer springs, whereas if single bonds are longer, they're longer, less stiff springs. And a smaller, tighter spring will vibrate faster than a longer, let's say, lankier spring. This is how you could think about this concept without using Hooke's law. And notice it's this exact trend that we see on our wave number chart. Notice the C triple bond has a wave number at 2100 to 2260. Here's the C double bond. It has a lower wave number. However, not on this chart is the C singly bonded to another C, but we can rest assured that it would be even lower than the C double bond C. Now, let's look at this example right here. Could we predict the relative wave numbers for a CO bond compared to a CH bond? Well, in the CO bond, we can say the carbon is bonded to oxygen, which is a heavier atom than hydrogen. So the CH bond has a lighter atom bonded to carbon. Remember, we saw in Hooke's law that mass is inversely proportional to wave number. Therefore, the heavier the atom, the lower the wave number. The lighter the atom, the higher the wave number. So we should see the CH absorption band at a higher wave number. And sure enough, going back to our wave number chart here, here is the CH bond and here is the CO bond. Notice the CH bond has a much greater wave number. However, while we're looking at this, let's talk about this OH bond. Notice his intensity. It's not only strong, but it's also considered broad. What does that mean? Well, this is the IR spectrum of a molecule that has an OH. We would see this band right here. Broad in this case means wide. Why does this band appear broad? Well, it's simply due to hydrogen bonding. And the more hydrogen bonding you have, the wider the intensity. Therefore, let's say if you have a sample that you put in the IR that has a very high concentration of OH, then we can expect a nice broad peak between 3200 and 3550. If you run the same molecule but at a lower concentration, you can see that range narrow. Now it's only 3590 to 3650. The lower concentration sample would have less hydrogen bonding. Now, let's take what we've learned here so far and apply it to some problems here. Here's sample problem 1. It says, in which molecule below would we observe a higher wave number due to the carbonyl group? So we're focusing on the C double bonded to the oxygen. But notice the difference here in these two molecules. This one on the right happens to have a double bond right here, which means that this molecule on the right has some resonance. Let's look at that resonance. Remember, we saw before that we're allowed to move pi electrons, and you could actually move these pi electrons this way. When you make that move, these pi electrons right here jump up on top of this oxygen. Notice what this does to the C double bond O. If we look at the resulting resonance structure, it turns it into a single bond. Now think about it. Would we get the same resonance for this molecule over here? The answer is no. Therefore, we would say that this C double bond O has more double bond character, whereas the carbonyl group in the molecule on the right has less double bond character. Remember, we discussed before in resonance that if one resonance structure has a double bond and the other resonance structure has a single bond, then the bond is neither single nor double, it's somewhere in between. So this molecule on the right has a C double bond O that's partially single, partially double. Which means if the molecule on the left has more double bond character, it means that it's a shorter bond. And if the molecule on the right has some partial single bond character, it should be a relatively longer bond. And remember, we learned the relationship between bond length and bond strength, and that is shorter bonds are stronger, longer bonds are weaker. And we've learned in this online lecture that the stronger the bond, the higher the wave number, the weaker the bond, the lower the wave number. So the answer is the carbonyl group on the left molecule would have a higher wave number. Which means this: if we looked at the spectrum for each one of these molecules, notice the top molecule right here, his carbonyl peaks right about here. Notice it is peaking at a higher wave number than the molecule below. So notice sometimes you gotta break out your resonance moves to compare wave numbers. Let's look at another example here, sample problem 2. In which molecule below would we observe a higher wave number due to the carbonyl group? So, same question here, but again, let's look at resonance. For the molecule on the left, we can actually, remember, move these lone pair electrons this way, and that would force the pi electrons in the carbonyl group to jump up on top of this oxygen. The resulting resonance structure would be this right here. So right away we can see our carbonyl group for the molecule on the left has some partial double and single bond character. But notice we get the same resonance for the molecule on the right. Again, these electrons can jump up here, the pi electrons can move up on the oxygen, and we end up with this resulting resonance structure. So at first glance we would probably think, well, the wave numbers should be roughly the same. But careful here, these resonance structures all rely on the fact that either the nitrogen or the oxygen has to give up electrons and move in that direction. And the question is, which atom is more likely to give up the electrons, or which atom is less likely to give up the electrons? Well, remember, think of electronegativity. Nitrogen is less electronegative and oxygen is more electronegative. If nitrogen is less electronegative, he's more likely to donate the electrons to the left. Whereas oxygen, being more electronegative, he's more likely to hold on to those electrons more tightly, therefore he's less electron donating. That means the molecule on the left will therefore have a greater resonance, and the molecule on the right would have less resonance. Which means the left molecule would have more single bond character for its carbonyl group, and the molecule on the right would have less single bond character for its carbonyl group. And less single bond character, remember, means shorter bond and therefore higher wave number. So our answer is the molecule on the right would have a greater wave number for its carbonyl group. In fact, again, comparing them side by side, notice you would see this same relationship right here. Let's look at another sample problem here. In which molecule below would we observe a higher wave number, this time due to the C single bonded to O bond? So for the molecule on the left, we're focusing on this bond right here. And for the molecule on the right, we're focusing on this CO bond right here. Notice here, molecule on the left has resonance. We can say that the electrons on that oxygen can fall this way and boot the pi electrons up. The resulting resonance structure would look like this, which means our CO bond in this case is partially double bond, partially single bond. Whereas in the other molecule, we wouldn't get that analogous resonance. The electrons on that O would not jump to the left. Therefore, the molecule on the left has less single bond character, giving the molecule on the right more single bond character, which means the CO bond in the left molecule would have a higher wave number, and the CO bond for the right molecule would have a lower wave number. So the answer is the molecule on the left would have the corresponding higher wave number for its CO bond. So what have we learned here? A lot of points here. Number one, we saw the stronger the bond, the higher the frequency or wave number. We saw the lighter the atoms, the higher the frequency or wave number. We also saw that OH absorption bands are broad due to hydrogen bonding. We also saw number 4, electron delocalization can affect the wave number of a functional group. And lastly, we saw 5, electron withdrawing or donating can affect the wave number of a functional group.